So once again, the topic is trigonometric integrals. Basically, as the name suggests, this is integrals that involve trig functions, but a whole bunch of combinations of trig functions. You know, so far we've done simple trig functions like integrating sine 3x or secant squared. But what if you put several of them together? How do you integrate it? There are different techniques that we're going to look at in that direction today. First of all, let's review what we already know. So a little bit review of the facts about trig integrals. Of course, we all know by now the integral of sine and cosine. Let's just begin with that basic integrals to remind everyone. So the integral of sine x dx is negative cosine, right? And the integral of cosine x dx is positive sine. And we also learn if you have constants like sine of 3x, in the final answer you're going to have a factor of 1/3, etc. Then we've also reviewed in the past things like the integral of secant x tangent x. What do we know about this integral? Secant x, because earlier we had seen the derivative of secant was secant tangent, right? Okay, we also reviewed on the first day the integral of tangent x. Does anybody remember the answer? This is negative ln of cosine. If you don't remember it, you can also always derive it by using u substitution, right? Write it as sine over cosine, let u be cosine. You can derive it, but it's good to remember that result as negative ln of absolute value of cosine x plus c. How about the integral of secant square? Tangent x, because derivative of tangent is secant square, right? Mm-hmm. Okay. Now, how about integral of tangent square? Any suggestions how we can do that one? Maybe we already talked about it on the first day. First, we need to rewrite it. Let's rewrite it as secant square minus 1. Now, how do I know that? Because there's a very important identity we should be familiar with. 1 plus tangent square x equals, does anybody remember this one? Secant square x. And there was a similar one. Let's also review that one. 1 plus cotangent square x equals cosecant square x. So right now I'm trying to rewrite tangent square in terms of something else. So go to the first equality and solve for tangent square, and you will have exactly secant square x minus 1. Well, did that help us any? Can we integrate this now? Easily, right? Integral of secant square is tangent x. And integral of negative 1 is just minus x plus c. So we know how to integrate secant square. We can also integrate tangent square. How about squares of the sine and cosine functions? We also reviewed this on the first day. So let's do both of those real quick. Sine square x dx. And we will also talk about the integral of cosine square x dx. Again, these formulas are really essential and important to be able to do well in this section. You got to make sure you have these down packed. You know them really well without having to look up a formula sheet, because everything we do in this section is going to depend on knowing these basic formulas. Okay, for the integral of sine square, does anybody remember that one? There's a little trick. Good. There was a power reduction formula for sine square, right? What was it? 1 minus cosine 2x all over 2, which I put outside of my integral sign. So now the 1/2 can stay, and you integrate the inside part. You get x minus sine 2x over 2 plus c. This other one is going to be very similar. I'm not going to solve the whole thing, but let's just remind everybody, what was the cosine square identity? What was the power reduction formula for cosine square? For sine squared, the formula was 1 minus cosine of double x over 2, right? For cosine squared, it was very similar. 1 plus cosine of 2x over 2. So we should also be familiar with these power reduction formulas. 1 plus cosine of 2x over 2. The over 2 part is taken outside, as you see. So once again, you could also do this one like the one above. The only difference will be there will be a plus sign in the middle. So you can do that one. Same answer as above, but there's going to be a plus sign in the middle. Okay, so now that we've reviewed these basic rules, we're ready to do combinations of things or higher power integrals using trig functions. Yes? I'll just put it. Right. There's just going to be a plus in the middle. So I'll let you guys finish that one. Okay, here is now some varied examples that make use of these rules. So some examples. Once again, your textbook has all sorts of formulas. What do you do with an odd power? It's an even power. Here we're going to try to use our intuition and not rely on the formula so much. Try to design a plan depending on the given question. So let's begin with this example. It's the integral of cosine to the 4x times sine x dx. When you have combinations of sines and cosines in an integral, you really have two choices. We're going to try to do those with u substitution. You know, you either let u be cosine x, or you let u to be sine x, right? Now, which one would work better in this case? Any thoughts? If we let u be cosine x, its derivative is negative sine x dx, right? And there is already a positive sine x dx there. Don't worry about the constants. We can always divide out by a constant, and like this negative, we can handle that. But make sure the rest of the expression is there. Now, what if I made the choice of let u be sine x? Then I would need to find a cosine x dx here, right? Well, I could separate that cosine to the 4 as cosine times cosine cube. I could get a cosine x dx, but then what are you going to do with the remaining cosine cube? It's not possible to write that in terms of sine. It gets more complicated. Always try to choose the one that seems easier to follow through. In this case, if you let me cosine, its derivative is negative sine x dx. It's already here. That is the best choice. So let's go with that. So let u be equal to cosine x. So du equals negative sine x dx. Now coming back to this integral, I'm going to replace cosine to the 4 with what? First, that part is just u to the 4th. We'll get to the other part in a moment. And how about sine x dx? Is it du or negative du? Because negative sine x dx is du, right? But I need to replace positive sine x dx with something. So what should I put? So it should be negative du. In other words, if you solve this equation for sine x dx, what would you get? Negative du, right? So replacing sine x dx, we should put a negative du. Okay, the rest should be easy, right? We took a very complicated looking integral. Now it's in terms of u. It couldn't be any easier, u to the 4th. So let's just go ahead and integrate that. So here we're going to have negative u to the 5 over 5 plus c. But don't leave the answers in terms of u, because you must replace the original variable into the equation. In this case, u equals cosine x. So I've got negative cosine, the 5th power of cosine divided by 5 plus c. By the way, is there a difference between this and this? Cosine to the 5 of x and cosine x to the 5th power. Are those the same things? Like when I write cosine squarish for shorthand, It's really the same exact thing as cosine x to the second power. But it's not the same as this, right? Cosine of just the x being squared, that's different, right? So it's just cosine squared is the same thing as cosine x times cosine x, basically. It's just a shorthand notation. Okay. So again, they're going to get more and more challenging as we do more examples today. Let's take a look at the next example. Cosine to the 4 times sine x. The integral of cosine to the 4 times sine. I'm sorry. I meant to say integral of cosine cube. Unless you want to do the same problem over and over again. Maybe on the Groundhog Day or something. Okay, so we're going to integrate cosine cube. We have no formulas, no power reducing formulas for the third power of cosine. Any thoughts? What could we possibly do here to integrate this? Any thoughts? Excellent suggestion. Let me just take the first part of your suggestion, which is, can we break it down as cosine squared times cosine? Okay, so let's write that down. We're going to rewrite this as the integral of cosine square x times cosine x dx. Okay. Now, if we bring in the power reducing formula for cosine squared, you still have to multiply that whole thing with cosine. It's going to get still very complicated. Okay, the power reducing formula is usually used when you just have even powers of cosine or even powers of cosine and even powers of sine. In this case, because you have a cosine x dx, consider this as your du. Okay, if this is your du, what would you want to let u to be? Don't even look at what we already have, but if your du is cosine x dx, what would you want to let u to be? Sine x. Now, how can you get a sine out of cosine squared? That should be easy, right? Because we know that sine squared plus cosine squared equals 1, right? So cosine squared equals what? 1 minus sine squared, right? So why are we bringing in the sines in here? Because we want to let u be sine, because we've noticed that its derivative is cosine x dx is already in here. So cosine squared we're going to write as 1 minus sine squared. Okay, and this may look weird right now, but as we do more examples, you're going to see this trick being applied over and over again. If you have a cosine x dx, you let that to be your du, or if you have a sine x dx, you let that to be your du, so that we try to put everything else in terms of your u variable. So in this case, cosine squared is 1 minus sine squared. I just wrote that identity. I haven't done my u sub yet. Okay, so now we're going to do u substitution. Let u be equal to what? Sine x. Why? Because its derivative is cosine x dx, and we already have a cosine x dx in there. Could you have done the opposite? Don't write this, please, but if I have let u be equal to cosine x, then du would be negative sine x dx. Do I have a negative sine x dx in there? Not really. I have sine square and things like that. But so this is not going to work. We're not going to choose that substitution. Instead, let u be sine x. Its derivative is cosine x dx. And now we can go with our integral. The integral is equal to, okay, so what am I going to write? Now I want to be able to write just the u and no other variable, just the variable u. No x is allowed in this next step. 1 minus u squared, right, because we let u be sine x, right? So sine squared is the same as u squared, right? So we're going to put 1 minus u squared times what? Instead of cosine x dx, du. So once again, we have accomplished a great deal in those two steps. It turned out to be a very simple integral, just the integral of 1 minus u squared. Now, could I say the integral of 1 is x? Could I say that? Be very careful. Usually we say that, but now what is our variable? Our variable is u, right? You're integrating 1 with respect to u. So what should it be instead? The integral of 1 with respect to u is u. Minus the integral of u squared with respect to u, that will be u to the third over 3, right? And the last step? Exactly. Place the u back. So u is sine x minus u cubed. That'll be sine cubed, right? Plus c.
When these examples are done, how did you cancel out, like on this upstream, cancel out that cosine effect?
All right, here's our next example. Let's do the integral of cosine to the third times sine square. The integral of cosine to the third times sine square. I don't clearly see a cosine x dx or a sine x dx. So we're going to need to split something here. So we end up with a cosine x dx or sine x dx. Remember, that will be our du. And everything else will have to be written in terms of the other trig function. I'm going to give you a little bit of time. Try a few things. See if you get lucky. If so, it's a combination that works. And we'll discuss it in just a few moments. Okay. Okay, how do we do on this one? How did you begin? You split cosine cube as cosine squared times cosine. Cosine squared. I'm going to put my cosine at the end with the dx. And sine squared, we keep it as it is at the moment. Sine squared. Okay, this cosine x dx, I'm going to use as the du. If that is my du, what should u be? Sine. That means everything else must be written in terms of the sine function. Okay? Now, how can I write cosine squared in terms of the sine? 1 minus sine squared. And then we already have another sine squared. Again, this I'm reserving for my du. So let u be equal to what? Let u be equal to sine squared or just sine? Just sine. Because then and only then will the derivative be cosine x dx. So let's kind of look ahead a few steps and then we can go and do the work. So the cosine x dx part, that's my du, right? The 1 minus sine squared, how will you write that in terms of u? 1 minus u squared. Multiply with on the outside of the parentheses, u squared again. And that will be an easy integral. No trig functions involved. We will be able to integrate that easily. So let's do it. So since u is equal to sine x, replace all the sine functions with u, or powers of u, of course. You can, but I like to do it in the next step. You can do it now if you like, but I will do it in the next step. Now I will distribute. Now let's integrate each piece one at a time, right? What could be easier, right? And finally, put the u back in there. So we got sine to the third x over 3 minus sine to the 5x over 5 plus c. Okay, I want to ask you, could I have done the same problem? Instead of separating on the side a cosine x dx for my du, could I have done this problem with separating a sine x dx on the side for my du? Could I have split a sine x on the side? What would be the problem then? You know, in the beginning I could certainly split sine squared, sine times sine, and one of them I could separate as sine x dx being my du. But what would be the problem with that? Does anybody see a problem with that approach? There'll be an extra sine x. Now you have to convert everything into cosines, right? If your du is going to be sine x dx, then your u has to have a cosine. Is it possible to convert sine x into cosine x? Not easily, right? Sine squared, there's an easy way to convert that into cosine square, right? Even powers of sine can be converted into even powers of cosine easily. So in this problem, you really didn't have a choice. You had to separate cosine x dx. In the future, how can we recognize this in a problem? We look at a problem, how can we know, oh, I'm going to separate a cosine x dx? Because look at the power of the original cosine. It was an odd power, right? If you split the odd power of cosine as cosine times cosine square, we know the cosine square can be converted into sine square easily. And then cosine x dx can be reserved as a du. Okay, so usually when you have an odd power, it's a good idea to split that one as cosine times cosine to the even power. Yes, James?
Can you use integration by parts for this?
You could try to use integration by parts. However, the moment you're trying to, if you let like let's say u be equal to cosine cubed, its derivative is going to be very complicated. It's going to be 3 cosine squared times negative sine, and the integral of sine squared will be complicated. So I wouldn't recommend it. You may get stuck at one point anyway. So u substitution is really the best way to solve these questions. Okay, we'll do another example. Okay, another one with sines and cosines, and then we're going to look at secants and tangent combinations. Let's take a look at this example. That's the next one. Let's see, do we have a number? Don't remember. So let's just say another example. We're going to integrate cosine to the 5th power times the square root of sine theta d theta. And the variable doesn't matter. They could have put x instead of the theta. They could have put t or y. You know, it just doesn't matter what variable they've used. Once again, I'd like to give you a few moments to work on this before we put the solution on the board. Okay, let's take a look at the solution together on the board. Okay, so because of the odd power of cosine, and because the sine is trapped under the square root sign, I'm going to reserve a cosine theta d theta for my du. So I'm going to split cosine to the 5 as cosine to the 4, and the other cosine I place at the end. Over here we have the root of sine theta. So if I want to reserve this for my du, already I have a plan here. If cosine theta d theta will be my du, what should my u be? I want to let u be sine theta so that du can be cosine theta d theta. What this is telling me is I got to have everything in terms of sine, and the du is already there, right? But everything else must be written in terms of sine. Well, cosine to the 4 can be written as cosine square times cosine square, right? So I'm going to write cosine square in terms of sine square, which is 1 minus sine square, right? Times another cosine square, I could really do this. Just square that. Times root sine theta, cosine theta d theta. This is where I'm going to put everything in terms of u. Remember, u is sine theta. Okay, so now I have an integral that doesn't have any trig functions. All it has is an algebraic expression in terms of u. I was asked earlier, can we integrate the first part separately, the second part separately, and then multiply? What is the answer to that question? No, we cannot do that with multiplication, right? If you're adding things, you could go one piece at a time and integrate. If you're multiplying things, there is no multiplication rule for integration. That's what makes integration so difficult in a sense. So first we must distribute u to the, this binomial actually. Let's first distribute our binomial. Okay, so this is the integral of 1 minus 2u squared plus u to the 4 multiplied by u to the 1/2. Now let's distribute u to the 1/2. That's u to the 1/2. Okay, when you're multiplying u squared times u to the 1/2, you add the powers, right? So now the power should be 2.5 as a fraction that is 5/2. Plus u to the 4 times u to the 1/2. Add the powers. That's 4.5, right? As a fraction, how would you write that? 9/2. Now let's integrate it. So get u to the 3/2 over 3/2, which is the same as times 2/3. U to the 7/2 over 7/2, or times 2/7. U to the 11/2 over 11/2, or times 2/11. And all I have to do now is what? Plug in u, and what was my u? It's been so long I forgot. U was sine theta. So let's go back and put u equals sine theta. By the way, you could do it the way that I did it, or you didn't have to use these parentheses around sine theta, right? You could also write, for example, the last thing you could have written sine to the, right there, 11/2 of theta, or put the parentheses around it, put the power on the top. Again, either one is the same thing. I have to say, maybe this is one of the more challenging questions, one of the most challenging ones you're going to see in this section. So if it looked like it was a little bit difficult, don't be discouraged, because it was pretty challenging.